1.6 reviews common functions that you need to have memorized. So you need to know what the graphs and the equations for each of these common functions look like, and then also transformations of those functions. Okay, so first of all, the functions that we need to know, the first one is the constant function, which is just y equals a constant or f of x equals a constant. Second here, all right. And so here, that is just a horizontal line for some value of c. The domain for this is all real numbers, or from negative infinity to infinity, and the range is just at y equals c, because that's the only output. It is not increasing anywhere, it is not decreasing anywhere, it is constant everywhere on negative infinity to infinity. And this is, so remember, even symmetry means we can reflect over the y-axis. Odd means we can rotate around the origin. Any type of y equals a constant function, we could fold on the y-axis, so, and it would land on itself, so it is an even function. Okay, for the identity, that's a typo. That should be the identity function, f of x equals x, or y equals x. This is a line with a slope of 1 and a y-intercept of 0, meaning it passes through the origin. The domain and range are all real numbers. And it is increasing everywhere and decreasing nowhere and constant nowhere. And it is an odd function because we could rotate it 180 degrees and it would land on itself. Now, this doesn't mean that all linear functions are increasing everywhere or odd functions. It means that just specifically y equals x is, and then anything else, any other linear function would be a transformation of that, like a shift or a stretch, that kind of thing. Okay. The absolute value function is y equals, or f of x equals absolute value of x. This is a function that we can write as a piecewise function, and we would split it as the output being the same as the input, x, when x is greater than or equal to 0, or the opposite of x when x is less than 0. So if I put in a 7, 7 is it part of this domain, so the output is the same. Output would be 7, so there would be a point at 7, 7. If I put in -3, -3 is in this part of the domain, so if I put -3 in, the opposite of -3 is +3, which is what happens when you take the absolute value of a negative number. It switches signs, okay? So this is the piecewise version of the absolute value of x. They are exactly the same thing. Now, the reason I show you that is because this shows us that the absolute value function is actually just a piecewise function of two linear functions, y equals x on the right side and y equals -x on the left side, okay? The domain is, again, all real numbers, and the range is from 0, inclusive, to infinity. This function increases on the interval from 0 to infinity. Again, doesn't matter if that's open or closed, and it decreases from -infinity to 0, and it's not constant anywhere. And then, again, this is an even function because we can fold it on the y-axis. Okay, the next one here is a quadratic function, okay? This is, we call this shape a parabola, and so this is the parent function or the standard function, y equals x squared, okay? The domain is all real numbers. The range is 0 inclusive to infinity. It is increasing on 0 to infinity. It is decreasing on -infinity to 0, and it is constant nowhere. And once again, we have an even function. Okay, for this one, this is the square root function, f of x equals root x. If I were to take the, if I write this as, let's say, y equals x squared, and then I switch the x and y, in other words, I make the inverse function, I would have x equals y squared, and then to solve for y, we'd take the square root of both sides, and we would have y equals. Now, if I'm taking the square root, remember I would have to put a plus or minus in front of that. However, that's not a function because it fails the vertical line test. So when we take just the top half of that sideways parabola, or that inverse of the quadratic function, then we get the square root function, which is just y equals root x. But again, this is the top half of the parabola, or if we reflected this over the line, y equals x, okay? And so now it is a function because if I included the negative part, it would fail the vertical line test. The domain is inclusive, 0 to infinity. The range is the same. It is increasing on that entire interval. It is decreasing nowhere. It is constant nowhere. And it is neither even nor odd. So I'm just going to do that. Okay. All right. The parent function for a cubic polynomial, y equals x cubed, or f of x equals x cubed, looks like this. And the domain is all real numbers, so negative infinity to infinity in interval notation. The range is the same. Okay, and it is increasing everywhere. Even though right at 0 it looks like it flattens out, it really doesn't. Any point, like the point at 0 is lower than any point that's to its right, and it's higher than any point that's to its left, even though they're very, very, very close. Like it might be 0.00000001. Okay, but it is still increasing everywhere. Okay, it is decreasing nowhere, it is constant nowhere, and this one is an odd function. Okay, and then the inverse of the cubic function is the cube root function, which looks like this. Now, this one, when we take the cube root, we don't have to put a plus or minus in front of it because it's an odd index. Okay, so because of that, I have the inverse of this entire function, and again, that's what I would get if I reflected this line over, or sorry, this curve over y equals x, that line right there. I would have the inverse, which is this one right here. Okay, so the domain and range are the same. Still negative infinity to positive infinity. It is increasing everywhere, decreasing nowhere, constant nowhere, and it is odd. Okay, so those functions you need to have memorized. They're going to come up a lot. We're going to use them a lot. You need to know what that parent function looks like. You need to know its domain and range, and then you need to be able to apply transformations. So that's the next part we're going to look at, is transformations. If we take a function and we add a constant to the outside of that function, so notice here we've got plus c or minus c, then we have a vertical shift. Now, I'll be honest, I do not like writing this at all, because if we really should just look at this one and say, if c is positive, we shift up. If c is negative, we shift down. So honestly, I'm going to tell you to ignore this completely. But when you give a shift, you should give the number and the direction. So if I had y equals, let's say, absolute value of x minus 3, I would say that's the absolute value graph shifted down 3 because we have a negative value there. Okay. So again, this is a vertical shift by a number c, so that's going to be up or down. And then a horizontal shift happens when we add or subtract inside. Once again, I do not like that the book uses two different representations of this. Really, you just need to think, if you have a number that is being added or subtracted inside the function, then that is a horizontal shift. And then we say if c is positive, actually, no, let me back up. This is the one I want to keep. This is the one I want to get rid of. Okay, I'll explain why in a second here. So if c is positive, we move to the right, and if c is negative, we move to the left. So this is the reason I'm doing it this way. C is the value that gets subtracted from the x coordinate. So if I see y equals, let's say, x minus 3 squared, that is y equals x squared. That is, and I'm subtracting 3 on the inside, so that means c is a positive number, and I am shifting to the right by 3. Okay, but we really should be in the habit of thinking of it as what is being subtracted from x. Okay, once again, I don't want you to think about like the like two different rules here. Just think, if I'm adding or subtracting something from the x, then that's a horizontal movement. If I am subtracting something from x, then I move to the right. If I'm adding something, then I move to the left. Or in other words, if c is negative. Okay. So we're starting with the square root function, y equals, or f of x equals root x, and we're graphing transformations of that. So this one right here, I see that inside the function we are adding 5. So if I write it in terms of f of x, I would write f of x plus 5, because the x is being replaced by an input of x plus 5 to get this. So because I am adding 5 on the inside, that's the same thing as subtracting a negative 5, and a c value of negative 5 means I shift to the left by 5. So my original square root function, make this graph a little bit bigger, would start at the origin. Come on. Okay. So this is the original. I would start at the origin, and then it would pass through 1, 1, It also passes through 4, 2. So this is the graph of the original. And I'm just kind of showing where we started. And then we are going to shift to the left by 5. So this vertex, 1, 2, 3, 4, 5, comes over here to negative 5, 0. And then I have a point there. I go up 1, 1, 2, 3. So it looks like that. Okay. Next one, here I have plus 3. Notice that this is not extended across here. Okay, so this plus 3 is on the outside of the function. So this is f of x plus 3. Because that is positive, that means my y value I'm adding 3 to, so I'm shifting up by 3. Okay, so again, we have this starting one. I drew it over here, but that vertex is going to go up to the point 0, 3. And add a few more points of accuracy. And it's going to look like that. Okay. This one over here, we are subtracting 2 on the inside of the function. So this is f of the quantity x minus 2. Okay. So instead of a vertex at 0, 0, I have a vertex. So my c value here is a positive 2. So I'm going to go to the right. 1, 2. And then for more points of accuracy, I'm going to fill that in, and there we go. Okay, at this point, if you would like to pause the video, try a couple on your own, you're welcome to do so. All right, for this one, I'm subtracting 4, so this is f of x, and then minus 4 on the outside, so I'm going to go down 4. So my vertex goes down here, 1, 2, 3, 4, and then again, fill in a couple more points. Oh, missed a little bit, but you get it. Okay, looks like that. Okay, and then here I have a combination of those two things. So here, this tells me I'm going to go to the right by 3, and this tells me I'm going to go up by 1. So my vertex is going to shift to the right 3, 1, 2, 3, and then up 1 to here, and then fill in a little bit more. So there's my function. Okay, another type of transformation is a reflection. We can reflect over the x or y axis, or the words we use is about the x-axis or in the x-axis. There's several different prepositions you might see. They all mean the same thing. So if we are flipping across the x-axis, so think about a couple of points. If I have a point here, let's say at 2, 1, and then I flip it across the x-axis, it's still over here at 2, 1, 2, but instead of going up 1, I would go down 1, so it would be at 2, negative 1. So what we should notice then is the x coordinate is the same, but the y value changes. If I want to change the y value, I need to put a negative in front of the entire function, okay? Because y is my function, so I'm putting a negative out in front of that. So y equals negative f of x, or the opposite of f of x, gives us a vertical reflection across the x-axis. And then across the y-axis, we change the sign on the inside, okay? So x has the opposite sign. Again, let's say I started at the point 2, 1. If I reflect that across the y-axis, that would be the point negative 2, 1. So in other words, the x has the opposite coordinate. So stop that. Let's do a couple examples of reflections. Again, here's the parent function for y equals the cube root of x. Just to find a couple of points that have to be on the graph, we know that the cube root of 1 is 1, so it's going to have a point at 1, 1. And then also 8 is the next perfect cube. The cube root of 8 is 2. So these 3 points, 0, 0, 1, 1, and 8, 2, are kind of like the starting points, and then also negative 1, and negative 8, negative 2. These are kind of the starting points just to make sure you have some accuracy. I don't know if this graph goes, let's see. 1, 2, 3, 4, 5, 6. Yeah, this will go all the way to 8. So we can have those points to make sure that we have a little bit more accuracy than just starting here and going whoop, whoop, because that's not very accurate, despite the cool sound effects. All right, so reflecting in the x-axis means that I am now graphing y equals negative cube root of x. So I'm still starting at the origin. Let me make this a little bit bigger. So can I just make this bigger? Let's see. Yeah, we can do that. Okay, So I'm still starting with a point at 0, 0. And instead of going to the point 1, 1 and the point, let's see, 1, 2, 3, 4, 5, 6, 7. So this is 8. Instead of 8, 2, I'm reflecting those. So I'm at 1, negative 1 and 8, negative 2. Okay, so here's part of it. And then it's an odd function. So I can use symmetry, rotational symmetry around the origin to get the rest of it. So roughly something like that. Okay, and then for the y-axis, we are reflecting horizontally. So again, 0, 0 stays where it is. The point 1, 1 is now going to go to the point negative 1, 1. The point 8, 2 will go to the point negative 8, 2. And then we have this half, and then reflecting that 180 degrees. Okay, something like that. Oh, that one's better. Nice. Oh, proud of that one. Okay. You may notice that these are the same thing. Because we have an odd function, reflection in the x-axis and reflection in the y-axis are going to give us the same thing. Imagine we take this one and we flip it around 180 degrees. It would land on top of itself. And so that's why those two happen to be the same. That will not happen for all functions, just for odd functions. Okay, so that's reflections. The last piece is stretches and shrinks. And we can do this vertically or horizontally. Okay, first of all, if we have a vertical stretch or shrink, let me try and fit this on the screen here. If we are multiplying on the outside of a function by a constant, then whether that constant is bigger than 1 or smaller than 1 will tell us whether we stretch or shrink. If we are multiplying by a number that is bigger than 1, then it is a vertical stretch. If you took trig last semester, which most of you did, think about an amplitude change. We're multiplying by, like a 3 out in front, then that's a vertical stretch, because then we go from negative 3 to positive 3 on a sine function or something, rather than just negative 1 to 1. If we are multiplying by a number that is less than 1, okay, then we are shrinking, okay, because instead of, like again for a sine function or something, instead of a height of 1, we might have a height of only 1/2, something like that, okay. For horizontal stretches and shrinks, this is where, okay, so let me kind of explain why it seems like the rules are the opposite for x coordinates and for y coordinates. Really, it's because in y equals c times f of x, I could divide both sides by c and write it as y over c equals f of x, and this shows us that we are affecting the y coordinate, not the x coordinate, okay? And here we are dividing. The thing is, though, we usually isolate y when we write things in function notation, which is why that c gets multiplied by the other side, okay? Same thing with the adding or subtracting. When I had like y equals f of x plus c, really that would be y minus c, if we subtract that to the other side, equals f of x. So that shows us that we are shifting the y coordinate, not the x coordinate, because x coordinate shifts happen on the inside. So if you're ever curious of like, why does it seem like we do opposite things when it applies to the x coordinate or the y coordinate, or why does it seem backwards for the x coordinate? Really, it should be the same for both, but in function notation, we isolate the y and we move those values that stretch or shrink or shift to the other side of the function to apply to the f of x. Okay, so then for horizontal stretches and shrinks, once again, multiplying by a coefficient, if I have a number that is bigger than 1 on the inside, then this is a horizontal shrink, okay? Because really we're dividing by c, just like we would be dividing up here, except we move the c over, okay? And then if c is less than 1, now it does say greater than 0 because we're talking about positives here. We already know that the negatives do a reflection. But if we have a number that's less than 1, then that means we have a horizontal stretch. To compare to trig, think about how we change the period on a sine or a cosine function by doing 2 pi divided by the b quantity, which is the coefficient of x. Okay, so a couple examples here. So we just have a piecewise function with 3 line segments, and this says we want y equals 2 times f of x. So then the output is going to be twice the input, I'm sorry, not twice the input, twice the original output on this function. So here, this point's going to stay on top of itself because 0 times 2 is still 0. But then this point, 3 times 2 puts me at 6. So that point gets stretched up to there. This point, 0 times 2 is, I'm looking at the y coordinates, 0 times 2 is still 0. And here, negative 3 times 2, that's going to shoot down here to negative 6 because we're multiplying by 2. And then lastly, again, another 0. Okay, 0 times 2 is still 0. So I'm going to fill these in as the line segments. And there's our vertical stretch of 2. Okay, here's a vertical stretch of 1/2. Again, 0 times 1/2 stays 0. So all these points still sit on the x-axis. But this is now going to be 0, 3 over 2 because I'm multiplying by 1/2. So, or 1.5 if you want to do a decimal. And then same thing here, negative 3 times 1/2 would be negative 3/2, which is negative 1.5. So our shrink gives us this function. All right. Here we are multiplying by a 2 on the inside of the function now, so that's going to affect the x coordinate, but it's going to be a shrink, a horizontal shrink by 2, okay? Or we could say of 1/2 because we divide by 2, the same as multiplying by 1/2. Okay, so I'm looking horizontally now. I'm looking at the x coordinate. 0 divided by 2 is still 0. 2 divided by 2 is 1. So this point moves over here. 4 divided by 2 is 2. Okay, negative 2 divided by 2 is negative 1. And negative 4 divided by 2 is negative 2. Vertically, the heights of those points stay the same. So we still have this kind of parabolic shape and then the line segments. Okay, so there's our horizontal shrink by a factor of 2. Here we have a horizontal stretch. Okay, and I know it's a stretch because 1/2 is less than 1. All right, so 0, 0, I'm looking at the x coordinate, 0 divided by 1/2, which is the same as multiplying by 2, stays 0. This point, 2 divided by 1/2, or times 2 is 4, so that point's going to shift over here. 4 times 2 is 8, which is off of this graph, so let's say right about there. Okay, negative 2 times 2 is negative 4, so that comes to here. And then negative 4, 0, so 6, 7, 8. Once again, we're off the graph. Okay, so I have something that looks like a stretched parabola there, and then line segments here to here. All right, I know this video is kind of long. Sorry about that. This is the last one we're doing. This is kind of putting it all together. We do have an order that we can apply transformations. We're applying the order of operations to input values. So whatever goes in for x, like if I want to know what f of 3 is, I'm plugging 3 in for x, and I have to think about what order I would apply any of the computations to that. So I work from the inside out because, you know, parentheses or grouping symbols come first. I do any multiplication stuff, and then I do any addition or subtraction because I'm following the order of operations. So same thing applies with functions. The reason that we have horizontal shifting listed first is because when we think about a function that has several transformations, so I'm just going to use like a, b, c, d for my coefficients. Let's say I have something like this: a times f of, and then I'm going to write this bx minus c and then plus d. So the reason I do the horizontal shift first is because I actually need to write this inside part as f of b times the quantity x minus c over b, and then plus d. So then the first thing I'm doing, moving from the inside out with my order of operations, is I use the grouping symbols inside here. So I do the horizontal shift, then I do the horizontal stretch or shrink, which is this, okay? And then I plug that into the function to get an output, and then I multiply for any vertical shift, and then I add a constant, okay? So we're going to do this one step at a time, but really just what you need to think about in general, instead of trying to memorize something, is go from the inside out. Okay, so with this one, we're going to break it into steps. Okay, so with this one, I know that my parent function is f of x equals x squared, and I know that I have a horizontal shift on the inside here. I know that I have a vertical stretch and a vertical reflection, okay, x-axis reflection, and then I have a vertical shift. Okay, so I'm going to do this one piece at a time. I'm going to start with the x squared function, and I'm going to shift 1 to the, and this is going to be to the right. So this is right 1 first. So the original, let me just make the graph bigger. The original vertex was at the origin, and I'm going to now shift that to 1 unit to the right. Okay, and then over 1, up 1, over 1, up 1, 2, 3. That's to get a few points of accuracy, and then the reflection. So this right here is y equals the quantity x minus 1 squared. Okay. All right. Next thing we're going to do is we're going to do this. We don't have a horizontal stretch or shrink, but we do have a vertical stretch or shrink. Okay. And actually, yeah, we'll do this in 2 steps. So I'm just going to do the 2 first, a vertical stretch by 2. So this is going to be y equals 2 times x minus 1 squared, and then I'll do the reflection in the next one. So starting with the same one that we just drew, my vertex is still going to be at a height of 0, because 0, this is the point 1, 0. 0 times 2 is still 0. Okay, but this point, instead of going right 1, up 1, I'm going to go right 1, up 2, because I have a vertical stretch of 2. And then from here, and you can do this with coordinates if you'd rather, like this is the point 2, 1. Well, now it's going to be the point 2, 2. And then this point right here is 3, 1, 2, 3, 4. But now I'm going to be at a point of a height of 3, 8. Or I can do it this way, just by like counting from my previous point. I know on the basic parabola, I'm going to go right 1 and up 3 after that first one. So this will be right 1 and up 6. 1, 2, 3, 4, 5, 6, which does put us at a height of 3, 8. Okay, so again, doesn't matter which way you want to get to that. Now I'm going to think about this being an even function, but then shifted. And so I'm just filling in my reflection points over here. So I have kind of this skinny parabola that looks like that. Okay, next thing we're going to do is the negative that's in front of the function. So I'm going to take that one and multiply by -1 for all of my y values. Okay, let's make this graph bigger. Okay, so this is going to be y equals -2 times x minus 1 squared. Okay, so we had a point here at 1, 0. Right, that's that point right there. It stays there because when I reflect it over the x-axis, it doesn't move. But now instead of going right 1 up 2 and left 1 up 2, I'm going to go down. So the point at 2, 2 now goes to 2, -2, and then 3, -8. Okay, and then fill in the reflection points. Okay. And then lastly, we had a vertical shift of +3. So y equals -2 x minus 1 squared plus 3. Okay, so I'm going to take this whole thing and shift everything up by 3. So starting at the vertex, I'm going to go from the point 1, 0 to the point 1, 3. Okay, and then write 1 down 2, and then write another one and down 6. 1, 2, 3, 4, 5, 6. Or you can say I'm at, wait a second. 1, 2, 3, 4, 5, 6. Oh, yep, that's correct. Is that a 3? It was a 3. That was a 4 for a second. Okay, which is the same thing as if I took this and moved it 1, 2, 3 up. I'd be in the same spot. Okay, then filling in reflections on the other side of the parabola. Now this is no longer an even function, but the original parabola, is an even function. So it's kind of like I've shifted my axis to right here, and then that's what I'm reflecting over. Okay, there we go. All right, now you don't have to use, you don't have to do 4 different graphs, do it one at a time. But if you want to, you're welcome to. And otherwise, you can just say, hey, I just want to do all the transformations at once and start at a single point. Like I'm going to start at my origin. I'm going to shift it 1 to the right, and then I'm going to multiply it by -2, which means it's still at the same place. And then I'm going to shift it up 3. And that would put me, in the same spot because I would be right here. And then say, okay, now I want to take the point 1, 1 that I know is on my original function. I'm going to subtract 1, square it, multiply by -2, add 3. And I would be right here at this point. Okay, so you can do it all at once if you want to. I think it's easier to kind of break it into pieces.